Good afternoon, class. So, last time we have seen some interactive part regarding the beta blockers. Now we will go to the next part, that is the structure activity relationship of beta blockers. So, regarding the beta blockers, we have already studied that the beta blockers or the structure of beta blockers is similar kind of structure what we can find in the adrenergic agents. Only we have to make some slight modification so that the drug becomes antagonist. But the basic structure or the basic nucleus somewhat it remains as the beta adrenergic agonist. Okay, so this is the structure of adrenergic agonist what we have studied. We have studied the SAR regarding that one. That is the adrenergic agonist. So this is the structure of adrenergic agonist. Here they have mentioned R3 and R4. If these R3 and R4 they are the hydroxy group, okay, R3 and R4. If they are the hydroxy group, then the given drug becomes adrenergic agonist. Okay. As the adrenergic agonist, they consist of the catechol nucleus. So catechol means there is a two hydroxy group on nearby carbon atoms with the benzene ring. So similar, if R3 and R4 they becomes or we attach the hydroxy group to this position, then the nucleus becomes catechol nucleus, and in case of catechol nucleus we will get the drug which are agonist to the adrenergic receptor. So if we have to change the agonist drug into the antagonist part, that is agonist to the antagonist, so we have to modify this catechol nucleus, or this we have to change this hydroxy group, or we have to remove this hydroxy group. So what is the way or what is the procedure to remove this hydroxy group? So first part regarding the SAR, if we replace the hydroxy group by SO2 NH2 group or CH2OH group or any other group which will produce the antagonist effect, so there is a possibility that we can replace one of the hydroxy group with sulfonamide group or CH2H group or any other group. It can produce the antagonist effect. So if such groups they are introduced instead of one of the hydroxy group, then the drug becomes antagonist effect. Or second way, what we can do, we can remove the hydroxy group. एकतर हायड्रॉक्सी ग्रुप एक हायड्रॉक्सी ग्रुप ठेवायचा, दुसऱ्या हायड्रॉक्सी ग्रुपला वरचे सबस्टिट्यूशन करायचे लाईक CH2OH SO2 NH2, किंवा हायड्रॉक्सी ग्रुप आपण काढून टाकायचे. At that time the drug becomes antagonist. The next part, the two carbon chain. So here these are the two carbon chain. So this two carbon chain is essential or it is important for the antagonist activity also. So this alkyl chain or ethyl group they were important for the agonist activity. So as well as along with the agonist activity, regarding antagonist activity also, if we modify the hydroxy group, then this it will increase the antagonist activity drastically. Okay. Then second part, if on this R2 or this nitrogen, if it having the larger alkyl groups, then the drug becomes beta antagonist, or the activity of drug converts into the beta antagonist. So it is depending upon the first part, we have to replace the catechol nucleus with SO2 NH2 group or CH2H group, or we have to remove one of the hydroxy group. At that time the drug becomes more antagonist. Second thing, if we can introduce the OCH2 between the aryl group or the aromatic ring and the side chain, that is the alkyl chain, then the drastically increases the antagonist activity. Or on the nitrogen, if we have introduced the bulky group or the larger group, then also the antagonist activity will increase. So these are some modifications. These are the points which comes under the SAR, which separates the adrenergic agonist from the antagonist. So that is the main difference between the adrenergic agonist and antagonist. Actually, their structure is nearly same, but these are some modifications we have to perform. For that, the drug can convert from agonist to the antagonist. The next part regarding the antagonist, the agonist drug structure, it becomes like this one, that is, it becomes the basic nucleus like this one, that is ARX CHOH CH2 NHR. So that is the agonist. It becomes antagonist with this basic nucleus. So here similar kind of structure what we can see in the agonist. So similar structure, with the help of aromatic X we are making them as a basic nucleus for the beta antagonist activity. So this aromatic group already we have discussed, it should not be catechol nucleus. ते कॅटेकोल न्यूक्लियस त्याच्यामध्ये कॅटेकोल ग्रुप असता कामा नये, हायड्रॉक्सी ग्रुप असता कामा नये. सो तो ऑरेल ग्रुप कोणता असावा? सो इट मे बी द फिनाइल रिंग or heteroaromatic ring. So this catechol nucleus, instead of catechol nucleus, there must be presence of a phenyl ring or heteroatomic ring, or it can be a naphthyl ring or substituted naphthyl. So in case of naphthyl or substituted naphthyl, they produces non-selective beta blockers. So they can bind to the beta 1 as well as the beta 2 receptor. They will not become the selective due to the naphthyl group substitution or substituted naphthyl substitution. The drug becomes non-selective. So that is about the AR. Then X we have already discussed, the linkage between the aromatic ring and the side chain or the alkyl chain. It can be OCH2, and if this can be OCH2, the drugs becomes aryl oxypropanol amine. And when the drug is aryl oxypropanol amine, in that drug the configuration of that drug, it must be S configuration to produce, or S configuration drugs having more activity as compared to the R. Generally 100 times more activity of S configuration drug as compared to the drug having the R configuration. And if this X is H, म्हणजे कुठलेही मध्ये सबस्टिट्यूशन करायचं नाही, डायरेक्टली aromatic ring to the 2 carbon chain मध्ये कुठलेही सबस्टिट्यूशन न करता आपण जर ड्रग तयार केले, so that drug it becomes aryl ethanolamine. And this aryl ethanolamine, this drug becomes non-selective, and with in this drug the R configuration drug are more active as compared to the S configuration. So are you getting the point? Are you getting the difference between the X is equal to H and X is equal to OCH2? If X is equal to H, it produces the antagonist activity, but when X is equal to OCH2, the drastically antagonist activity will increase. And in case of X is equal to OCH2, the S configuration drug with X configuration, it will show better activity or 100 times more activity as compared to the R configuration. But if the X is the hydrogen, then the drug becomes non-selective, and at that time the R configurated drugs, they becomes 100 times they becomes more potent or more active as compared to the S configuration. So that is the difference between X is equal to H, X is equal to OCH2. If X is equal to H, the drug is called as aryl ethanolamine. If X is equal to OCH2, the drug is called as aryl oxypropanol amine. Okay, so here you can find out this one. This CHOH is there. So this carbon, they are having the 4 different groups which are attached to this carbon. Okay, एका साइडला हायड्रॉक्सी ग्रुप आहे, एका साइडला हायड्रोजन आहे, एका साइडला ARX आहे, एका साइडला CH2 NH further group आहे. So they are having the 4 different groups which is attached to this carbon. Okay, when such condition is present, it produces the isomers. So if such groups is present, it produces the isomer. At that time, S isomer is more active in case of aryl oxypropanolamine, and R configurated compound or R isomer is more active in case of X is equal to H. आपण म्हटलेला मगाशी R S configuration हे कधी फॉर्म होतं, त्यावेळी CHOH मधला जो कार्बन असतो, it becomes the asymmetric carbon. so it is attached to the different 4 atoms, that's groups, it becomes the asymmetric carbon. And due to the asymmetric carbon, what happens? They having the different isomers. So in case of isomers, the R isomer is more active in case of X is equal to H, and S isomer is more active in case of X is equal to OCH2 groups. Are you getting my point? My point clear, Zara? And finally, NHR. So R can be isopropyl, tertiary butyl, aryl or alkyl group. They increases the polarity, they will increase the antagonist activity. So R group can be the isopropyl, it can be tertiary butyl, it can be aryl alkyl, so that the polarity of drug increases. Along with the polarity, the activity or antagonist activity of drug is also increases. Okay, so we will see one by one. Now the beta blockers, they are becomes of two types. If X is equal to H, second one if X is equal to OCH2. Now if X is equal to H, the drug becomes aryl ethanol amine. Okay, so here you can find the difference. So this drug isoproterenol. So you can find the structure of isoproterenol and isoproterenol. Both the structures are same, but only difference is that here hydroxy group is present, here Cl group is present. So due to the removal of hydroxy group, due to the addition of chlorine group, the drug becomes some kind of antagonist activity. But it was found that the drug does not become the completely antagonist, it having the partial antagonist effect. That's why clinically this drug is not used. But it is important because it is the first drug which having some kind of antagonist activity. Okay, so पहिला जो प्रयत्न केला सायंटिस्टनी तो काय केला, 2 हायड्रॉक्सी ग्रुप रिमूव्ह केले, तिथे 2 क्लोरीन ग्रुप अटॅच केले. So the drug becomes dichloroisoproterenol. So that dichloroisoproterenol, the drug, they having a partial antagonist activity or partial agonist activity. That's why they cannot be used clinically, because they require the complete antagonist drug. Okay, so it is not used clinically. Next part, the removal of 3 hydroxy group and replacement of 4 hydroxy group with methyl sulfonamide, it gives potent antagonist. So already we have discussed, ह्यापैकी एक methyl hydroxy group remove करायचा, दुसऱ्या ठिकाणी we can attach CH2OH, we can attach SO2NH2. At that time it gives the potent antagonist drug. Okay, for example sotalol. So that sotalol drug, if go through the structure, you can find out all the structure is same. इथला जो hydroxy group आहे, हा hydroxy group आपण remove केलेला आहे, and instead of this hydroxy group we are attaching SO2NH group. It is in the form of CH3SO2NH group. So drug becomes sotalol. It is the potent antagonist effect. So this substitution, it makes it more potent antagonist. That is, sotalol is more potent antagonist. So instead of SO2NH, we can also add the para-nitro substitution. हा ग्रुप काढून तिथे आपण नायट्रो सबस्टिट्यूशन पण करू शकतो. ओनली द effect on A substitution, that is the terminal amine group is present. So what will happen if any substitution can be done on amine group? That is the next part of SAR regarding the aryl ethanol amine. So we have seen we are moving from agonist to the antagonist basic nucleus. From antagonist we are moving to the aryl ethanol amine, which is the one of the antagonist structure. In that we are moving to the effect on N substitution. So here this nitrogen is secondary nitrogen. Okay, if this hydrogen which is present on nitrogen, if this hydrogen is replaced by CH3 group or any other group, then the drug becomes disubstituted or nitrogen disubstituted drug. At that time the drug becomes inactive. That's why this nitrogen must be having the secondary nitrogen or secondary amine instead of tertiary amine. तिथला जर आपण हायड्रोजन काढला तर काय होणार, tertiary nitrogen मिळणार. When the nitrogen becomes tertiary, the drug becomes inactive or ineffective drug. Then second part, alpha methyl group reduces activity. So this is the alpha carbon. So if we are attaching alpha methyl group, at that time the activity will reduce. Okay. Then 4 carbon containing alkyl group, the drug becomes active. So here 3, if we are attaching one more, the drug becomes active compound. So 4 carbon group or the 4 carbon containing alkyl groups we can attach. Or open chain, it can produces more activity as compared to the cyclic alkyl chain. He is a alkyl chain hai, he open chain hai, it produces more activity. Instead of attaching any cyclobutane or cyclopentane like structure, cyclohexyl like structure, that activity becomes less. And finally, regarding the end substitution, if hydroxyphenylethyl, methoxyphenylethyl or phenylethyl group at nitrogen, it gives more active antagonist drug. Okay, so this is the SAR point regarding the effect on M substitution. पहिलं म्हणजे N हा सेकंडरी असला पाहिजे. दुसरं तिथं ब्युटाइल ग्रुप असेल तर ऍक्टिव्हिटी चांगली दाखवते. त्यानंतर instead of cyclic structure, if the straight chain compounds are present or open chain compound are present, they are showing more activity. And finally, the hydroxyphenylethyl or methoxyphenylethyl at nitrogen, it gives more active compound. Okay, so this is about the substitution on N. Now the next class of the beta antagonist, when OCH2 group is present. Okay, that is the aryl ethanol amine मध्ये फक्त तिथं H होता. Here aryl oxy मध्ये OCH2 group is present. Okay, so para substitution on phenyl, it produces the selective blocker. And if aryl group can be naphthyl or substituted naphthyl, they use the non-selective blocker. हे फक्त एकच aromatic ring असेल आणि इथं जर तुम्ही substitution केलं, para substitution, drug becomes selective blocker. पण aryl group हा naphthyl group असेल, aryl group काढून तिथं हा naphthyl group attach केला, so the drug becomes non-selective blocker. So if para substitution groups are present, it shows selective blocker. If naphthyl groups are present, the drug becomes non-selective blocker. For example, pronethalol, propranolol. Write down the structure of these two. प्रोनेथॅलॉल मध्ये OCH2 नाही आहे, प्रोप्रेनॉल मध्ये OCH2 आहे. That's why propranolol is more active and more potent as compared to pronethalol, because they are having the OCH2 group. Other all the structures they are having the similar kind of structure. So write down these two structures. Now regarding SAR of that part, when OH is X is OCH2, then para substitution of aryl ring and no substitution on meta. This is the para position. This is meta. जर मेटाला कुठलेही सबस्टिट्यूशन नसेल आणि फक्त पॅरा पोझिशनला जर सबस्टिट्यूशन असेल, ड्रग बिकम्स मोर सिलेक्टिव्ह, दॅट इज द कॉर्डियल सिलेक्टिव्ह बीटा 1 antagonist. When there is a substitution on para position and there is no substitution on meta position. The next part, if catechol nucleus when substituted with methyl sulfonamide or CH2 double bond CH2O or amide, it gives the potent antagonist. So here you can observe this hydroxy group, it is converted into the OCH2 CH double bond CH2. So at that time it becomes potent antagonist. Hydroxy group असेल, it becomes agonist. But if we are replacing the hydroxy group with any other group, the drug becomes potent antagonist drugs. For example, oxprenolol. So in case of oxprenolol, they having the CH double bond CH2 CH2O, that is this group is present. At that time the drug becomes more antagonist as compared to hydroxy group. Then last part of the SAR, aryl ring may be heterocyclic or bicyclic ring. It produces optimum antagonist activity. So here you can observe timolol here, here. So they having the heterocyclic or bicyclic ring. At that time the drug becomes more potent, or they having the optimum potency as compared to other drugs. This is the structure of timolol, this is the structure of pindolol. Please write down the structure. स्ट्रक्चर काढा दोघांचं, टायमोलॉल अँड पिंडोलॉल. Okay, so this is the heterocyclic, this is the bicyclic ring. Okay, I have written. Now the last part of the SAR, it is drug with S configuration shows more activity, that is the 100 times more activity than the R configuration. So we have already studied that in case of X is equal to OCH2 or alkoxy group is present, at that time the drug with S configuration having 100 times more activity as compared with the drug with R configuration. And if X is equal to hydrogen, at that time drug with R configuration having more activity as compared to the drug with having S configuration. That is the important part. You should know better which configuration shows activity when. So X is equal to H, R configuration show more activity. X is equal to OCH2, R S configuration compound, it shows the more activity or the more potency as compared to the R1. Okay, so this is about the SAR for the beta blockers. There is a compulsory question on this part. Directly they are not asking the SAR, they will give the general nucleus. They will ask 1, 2, 3, 4. In that they will ask one point, what will happen if this is attached. So like this they will ask the question. Okay, so this is end of part, that is the SAR of beta antagonist. So these beta blockers, they are classified into three types. That is the non-selective beta blockers, that is the propranolol, pindolol, sotalol, timolol. Then cardioselective, that is the beta 1 blockers, which are the cardioselective. So that is atenolol, acebutolol, metoxolol, bisoprolol, ismolol, metoprolol, nebivolol. These all drugs which comes under the beta 1 selective drugs. So if the drug is selective, then only we can give for the cardiac treatment. If they are not selective, we cannot give for the cardiac, because they will also act on beta 2 receptor, so they will produce some kind of other side effects. So these drugs, they only bind to the beta 1 receptor, they will block beta 1 receptor, hence they can give in the treatment of cardiac functions or any problems regarding the heart. The next one, that is the alpha beta blocker, that is the mixed blocker. They are labetalol, carvedilol. These are acting on both, that is alpha receptor as well as the beta receptor. Okay, so these are structures: sotalol, S-butalol, ismolol. Okay, so from SAR we can come to know that naphthyl ring is present, then selectivity decreases. Okay. If butyl ring is present, then there is higher selectivity for the beta 2 receptor. When such groups are present at the para position instead of hydroxy group, they produces more selective beta 1 blockers. So from SAR you can come to know which drugs are selective, which comes or non-selective, depending upon the structure of these beta blockers. The next part, that is the mixed adrenergic receptor antagonist. So mixed means they can act on beta receptor as well as they can act on alpha receptor. So please keep in mind, selective alpha 1 blocker means which can block alpha 1 receptor. Non-selective alpha blockers means they can act on alpha as well as the alpha 2 receptor. Selective beta means they can block selective beta 1 or beta 2, but non-selective means they can act on beta 1 as well as the beta 2. And mixed blockers means they can act on alpha receptor as well as the beta receptor. So first drug, that is the carvedilol. Write down the structure of carvedilol. Again, here is asymmetric center, so they are having the R configuration as well as the S configuration, or you can say R enantiomer as well as the S enantiomer. So this is the non-selective beta receptor antagonist and alpha receptor antagonist. So they act on alpha 1 receptor, beta 1 receptor as well as the beta 2. So this is the mixed adrenergic receptor antagonist. Both the enantiomer, that is the R enantiomer and S enantiomer, they can antagonize alpha 1 receptor, but only the S enantiomer OCH2 असेल तर S enantiomer किंवा S configuration compound ची activity जास्त असते. So only S enantiomer possesses the beta blocking activity. They are generally administered orally. What is the use? Hypertension as well as the CHF, that is the congestive heart failure मध्ये carvedilol हा drug वापरला जातो. Next drug, labetalol. Please draw the structure of labetalol. Okay, so this labetalol is the non-selective beta receptor antagonist with potency somewhat less than propranolol. Propranolol पेक्षा याची potency कमी असते. Alpha 1 receptor antagonist with potency less than the phentolamine. And the beta blocking activity prevents the reflex tachycardia due to the alpha 1 receptor antagonist. It is generally administered orally or parenterally, and it is act as hypertensive drug in the treatment of hypertension. So you can observe hydroxy group catechol nucleus is there somewhat, so it produces alpha receptor activity, but at here also there is a CO2 NH2 amide group, so it may produce some kind of beta activity also, so it becomes the mixed adrenergic receptor antagonist. Okay, so this is about the mixed receptor antagonist, that is the carvedilol and labetalol, as they drug having the both the structures which are required for the alpha receptor blocker as well as the beta receptor blocker. So having the both the structures in their structure, or the both the groups in their structure, the structure becomes mixed, that is they can act on alpha 1 receptor, alpha 2 receptor, beta 1, beta 2, that means they can act on alpha receptor as well as the beta receptor, that means they becomes the mixed receptor antagonist. Okay, so this is about the beta receptor, their SAR, then classification of the beta receptor antagonist, and finally the mixed antagonist. Okay, so we will stop here. Remaining part we will see in the next lecture.